So let's go through one more example of identifying a surface, right? So here, our surface is given as a plane model. So there are, well, a lot of edges in this polygon. So there are 5 pairs of edges. So A is glued to A, B to B, and so on. And there are 4 unlabeled edges. And we need to figure out what this surface is, right? So the first question is whether this surface is orientable or not. So how do we decide that? So when we decide orientability, right? So we look at all pairs of edges with the same label. So like here, A and A, and then the counterclockwise direction is the positive. So we need to make sure that all pairs of edges that have the same label, they have opposite directions. So one of them is clockwise, the other one is counterclockwise with respect to the boundary of the surface, or of with respect to the whole polygon, right? So now if we look at this edge, so then at this A, then it goes counterclockwise, while this A goes clockwise. So which means they do have the opposite orientation. So specifically, this copy of A is actually A inverse. So if you write the fundamental, if we write the word for the plane model, then this is A inverse. And then we'll look at B. So and again, so one of these 2 copies of B is going to be B inverse. It's this one, and the other one is just B. So because its direction is the counterclockwise direction. Then C. So we have 2 copies of C. Then again, these 2 copies of the HC. So they, with respect to the plane model, so they have opposite direction on the boundary. So this is the positive. So this is the negative one. So this is the C inverse. Now D. So there are 2 copies of D, and this is D inverse, and the other one is just D. And finally E, and again there are 2 E's, and one of them is actually E inverse. So since all the 5 pairs of edges they appear in pairs where 2 edges in each pair have opposite direction along the boundary of the plane model, it means that the surface is orientable. So if at least one of them, if at least one pair of labels has 2 edges that appear to be in the same direction, then it is non-orientable, because then it means that there is an embedded Möbius band. So the next stage is to find the number of faces, the number of edges, and the number of vertices. The number of faces is always 1. It's just one polygon. So if your vertex is made out of 2, 3, or 4 polygons, then the number of faces is going to be more than that. But here it's just 1. Now, what is the number of edges? So here we have 5 labeled edges, A, B, C, D, E, and 4 unlabeled edges. And so 1, 2, 3, 4. So these 4 unlabeled edges, they're going to form the boundary of our surface. But currently, we just need to count them as edges. So there are 4 unlabeled and 5 labeled edges. So the total number of edges is 9. And then we need to find the vertices. So vertices is the hardest part. So how do we go about finding the vertices? So we just need to, so our polygon has a lot of, so how many vertices does the original plane model have? Well, I guess it is 10 plus 4, 14 vertices. So among these 14 vertices, so when we perform gluing on the actual surface, some of these vertices, so they're glued to the same point, and we just need to figure how many different points on the actual surface we are going to get. So let us count. So let me just write 1. So if this is vertex 1, then this one sits at the tail of edge A. So when it is glued to another copy of the edge A, so we have another tail of A, that is therefore also 1. But then here we see that 1 is also in the tail of B. So which means that when we glue B to B, this is also going to be 1 because it is in the tail of B. But now it is in the tail of E. And when we copy this E to the other E, well, this vertex is glued here because this is the other tail of E. Now this is also in the tail of C. So where is the other tail of C? It's here. So it is still the same vertex. So now when we, it happens to be in the head of B. So when we glue the head of B to the head of B, this is going to be the same vertex, and all these vertices labeled 1, they represent the same point on the surface. Okay, so now let's go about the head of A. So if this is 2, so where is the other head of A? So now this is the other head of A, 2. Now this is also the head of E. So now let's go to the head of E. Now this head of E is at the same time the tail of D. So now let's find another copy of the tail of D. So this is another copy of the tail of D. Okay, done. So now, which means that both endpoints of the edge A have been identified, so they're different vertices. So A joins vertex 1 to vertex 2. So now B joins 1 to 1. C, okay, so see the tail of C is 1, but the head of C is yet to be identified. So let me call this vertex 3. This is head of C. Now let's find another copy of C, and then we're going to label its head 3, 2. Well, but that's all, right? So because it's next to unlabeled edge. Okay, so now C connects vertex 1 to vertex 3. Now let's look at D. So D, the tail of D has been identified as 2. Now the head of D. So let's call this vertex 4. Now another copy of the head of D is here. So, and this is also vertex 4. Right? So which means that D goes from vertex 2 to vertex 4. Okay, and finally E, and E has been already identified. It goes from 1 to 2. So that's all. So the 14 different vertices of the original plane model, they represent just 4 different points on the surface. So which means that the number of vertices is 4. Okay, so now the faces, edges, and vertices have been counted. The next part, oh yeah, maybe from here, we know that the Euler characteristic of the vertex of the surface is the Euler characteristic if the surface is S is going to be 1 minus 9 plus 4. So which is 1 minus 9 plus 4. 1 minus 9 is negative 8 plus 4, negative 4. So the Euler characteristic is negative 4. Now, what is the number of boundary components? So how do we identify boundary components? So let's just look at, begin with some of the boundary components. So for example, this one goes from 1 to 3. So it goes from 1 to 3. So where is another copy of 3 that sits next to a boundary component? So next to an unlabeled edge. It is here, right? So 3. So which means that if you are moving from 1 to 3, then the next, you are going to continue here from 3 to 2. So where is another copy of vertex 2? Is here. And we are still going. From 2, we went back to 1. And that's it. So which means that this is our first boundary component. So maybe let me count. So the first boundary component. And at the same time, not all the boundary components have been accounted for. There is this which goes from vertex 4 to vertex 4. So this is boundary component number 2. So the number of boundary components is therefore 2. Okay? So now we know that the surface is orientable. Now we know that its Euler characteristic is -4, and we know that the number of boundary components is 2. So finally, these are the two possible equations for the Euler characteristic of the orientable surface and non-orientable surface, respectively. Since our surface is orientable, it means that we choose this formula and discard this. So this is because our surface is orientable. So now let us just treat it as the equation on G. So the left-hand side is the Euler characteristic is -4. So equals 2 minus 2. Sorry, my pen is not working properly. Minus 2G minus H. H is the number of boundary components. So the number of boundary components is 2. We have already found it. So -4 equals 2 minus 2G minus 2. So from here, we solve for G. And G happens to be, what is it? Is 2, right? So which means that the answer is an orientable surface of genus 2 with 2 boundary components. Or this is also the connected sum of 2 tori with 2 boundary components. So if you want an illustration, so it would look like something like this. So there are 2 holes, and the genus is also 2. But illustration is not necessary.